finally 10 a.m. and we can continue. Even now classes are virtual online, and still Thanksgiving week of Thanksgiving, right? Attendance is significantly low. Okay, anyway, we have to continue. And so you remember in the previous class, recitation class, we started discussing inductors, but we haven't finished them completely, right? So today we're going to finish introducing new material, and then we will look at examples. So you remember, we introduced inductance in this way, right? So if you take the total flux through a system, of course we usually use just a solenoid, right? If you take the total flux through these thousands of loops, total flux through the solenoid, of course it can be any object can be used to calculate its inductance. But anyway, total flux and divided by the current which creates this flux. So that ratio we called as inductance. And we introduced a special unit, SI unit, because this quantity is used a lot in electronics, right? So Henry, H capital. Okay, then again, as I said, this formula can be used to find inductance of any object. Solenoid, piece of wire, I know, car, whatever, right? So since it can be applied to find inductance of any, so let's apply and find inductance of a solenoid, because that's what we use most of the time, right? So we did it. We apply for a solenoid, and we found that inductance of a solenoid, basically we found flux divided by the current, you remember, and we ended up with mu naught n squared and number of loops, total number of loops in the solenoid, times A, which is cross-sectional area of the solenoid, and divided by L. L is just the length of a solenoid. And again, the major feature of this formula is that it depends only on the geometry and material inside of the solenoid. It doesn't matter what's the current flows, what's the current in the solenoid, or potential difference across the solenoid, or magnetic field inside. None of those. Only material, mu naught. It tells us that it's a vacuum right now inside of the solenoid. And geometry, number of loops, cross-sectional area, and the length. Okay, so after that, we decided let's look at the potential difference across a solenoid. So let's say current enters here and current leaves here. So enters, right, and here it leaves. So we wanted to find what will be the potential difference between this point, final point, where current exits, that's the final point, and initial point where current enters, initial point. So V final minus V initial. That's what we decided. That's what we decided to find. And again, I told you what surprises me, because effectively any solenoid is just a piece of wire, piece of an ideal wire we usually consider, right? And if you just have a straight piece of wire, then you're not going to get any potential differences across the wire, because it doesn't have resistance and it doesn't work as the battery. But once you wrap it in the form of a solenoid, it starts behaving in a different way, magically. So under certain conditions, of course, if you apply Faraday's law, under certain conditions you can get the potential difference. Mystery, right? Okay, so we derived at the end of the previous class, and we found. So we just grabbed this formula, total flux, right, and plug it here, and we ended up with this formula. So potential difference, again, this delta V, it's a V final, where current exits, minus V initial, that's what delta V. And again, I explained to you why we can use this formula, EMF equals minus d phi over dt, because what is effectively a solenoid? Solenoid, it's a thousands of loops. So we can apply Faraday's law. For one loop, it will be EMF1. Then for the second loop, then for the third loop, again the same EMF, then fourth, fifth, right, and all the way to 1,000. So you'll have thousands of EMFs. You just add them up, all right. So it gives you delta V, V final minus V initial. And when you add all those EMFs, which are each of those equals minus d phi over dt, you end up with the rate of change of the total flux. It's just simple calculus, right? So that's why we applied the same formula, and of course here phi, it's a total flux, which is the fluxes through each of the loops. Okay, anyway, so we started discussing this formula. Right, so let's continue. First part of the discussion. So, what if, okay, let me write, if current is constant. We discussed it, but let me review it again. If current is constant, then this is 0 di over dt, and the potential difference is 0. Delta V equals 0. It means what? It means if you're sending DC current, constant current, through a solenoid will be completely happy. It is not going to do anything. It is not going to produce the potential difference across itself, right? So potential here and potential, electric potential there will be exactly the same, right? So in this case, solenoid is a completely useless piece of useless element in a circuit. So if current is constant, and it doesn't matter how strong the current is, you can set, I don't know, thousands of amps, but again, if current doesn't change in time, or is not changing in time, delta V will be 0. Okay, then the next example we looked. So if current, no, not example, case, the next case. What if current is growing? Again, we discussed it, but I want to have everything on the whiteboard. So in this case, of course, di over dt is positive because current increases, delta change in time only positive. So di over dt is positive. So as a result, minus here, L is only positive number. L inductance cannot be negative. So minus L positive and di over dt also positive. So as a result, delta V is negative. So in this case, delta V is negative. And again, what is delta V? It's a V final minus V initial is negative, and it means that V final is less than V initial. Right. Okay, so it means that electric potential over here is smaller than the electric potential over there. Okay, let me draw another picture like I did in the previous class. So okay, so that's the solenoid, right? Again, this is final point, this is initial point, and this current I is produced by some battery over here, let's say. So this current, which is growing through the solenoid, is produced by this battery. So let me draw that current. I think I use blue. Right, so let me call it I, and I will add original, because there will be the induced current. Right. So this current I, it's that current, which is increasing. Right, and so this current changes. As a result, solenoid sees that current through the solenoid is increasing, and the solenoid produces the electric potential at the final point, and it's smaller than the electric potential at the initial point. So it produces lower potential and higher potential. And you need to understand, this is produced by a solenoid. It's not produced by this battery. Battery does something, it changes this current, and then solenoid starts responding to the fact that current changes. So basically it produces here a higher potential and lower potential, right? Okay, now, as a result, this additional potential difference will start driving an induced current. In order to get the correct direction of the induced current, I started using these words. Let's introduce an effective battery. So we can say that this solenoid starts working as a small battery with this polarity. So here we have plus, there we have minus. Small battery with a plus on this side and minus on that side. And as a result, what's the direction of the induced current produced by this solenoid? Yeah, plus minus, correct. So from plus to minus through the rest of the circuit. So induced current will flow this way. So this will be I induced. And now let me explain why I started after maybe a couple of years of teaching, I decided to add these words. Let's solenoid starts working as a small battery. Why? Because very often students write plus here, write plus there, minus there, and then as a result they remember the current flows from plus to minus, and they will drive this induced current from this plus to that minus through the solenoid, which is wrong, because this plus and the minus is produced in the solenoid, and then current is driven through the rest of the circuit. I've seen it very often in the past that students start drawing induced current, direction of the induced current in the wrong way. So that's why I decided to draw like a small battery, so that there wouldn't be a gap over here, and students would draw the correct direction of the induced current. Okay, so now that's production of the solenoid, this potential difference and this induced current. And now we need to develop some mnemonic rule which would help us to come up to the conclusion kind of faster. Because again, what is behind all this? It's a Lenz's rule. Faraday's law, all those words which we used in the previous classes can be applied here, right? So the loops doesn't like changes in the flux. If flux increases, of course it will drive the current in such a direction to suppress the flux. If flux is dying, it will drive the current in such a direction to support the flux. But now, since we're applying that for a more complicated system, many loops, so it's better to slightly adjust that Lenz's rule. So it will be easier, and we can apply it for this particular system only. So the rule now is this. So it's all about current instead of flux, right? Before, our system didn't like that flux was changing. Now the system doesn't like that current, this original current changes. So if original current is growing, the solenoid, the system, doesn't like it. It wants to have current constant. In that case, solenoid doesn't do anything. Right? So if current increases, the solenoid will wake up, right? Oh my God, you're changing current through me. So you're trying to increase the current, and I don't like it. So of course the solenoid will start driving its own induced current in the opposite direction, trying to suppress the growth of the original current. You see? So before the system was trying to suppress flux, but now it's better to state it in terms of current. If original current produced by this battery is growing, the solenoid will start driving current in the opposite direction, trying to suppress it. Of course, it wouldn't be able to suppress it completely, just to some extent. And of course, you can ask me, at the expense of what? That this solenoid can produce this potential difference, start driving an induced current. Everything costs money, right? So where is the energy? You remember when I introduced in the previous class inductors, which words I used? An inductor is a device which allows us to store energy in the form of the magnetic field. That energy can be used to drive this induced current in this direction, for example, right? So that's the rule. So if original current is growing, solenoid rebels. It will start driving current. Of course, first it produces this potential difference and start driving current in the opposite direction. Okay, so now let me write that. And again, it's just Lenz's rule, just restate it for this system, because it would be easier to analyze the system using playing with current, using current. Okay, so let me write that down. I'm just checking also if I mentioned everything. So I will write it this way. So the rule, let me write rule. So I induced tries to suppress I original. Damn it. Okay, let me add here I original. Okay, let me frame it. So drive the current in the opposite direction. Okay, so now that's yeah, and the example, right? I mentioned it in the previous class, but now let me remind you again. So simple example. Let's assume that you have a some circuit, some loop in the circuit, and let's assume that there is a constant current, let's say 1 amp, flowing in that circuit, in that loop, and let's say at a certain moment of time you open the switch. Again, if you don't know this, if you don't know Faraday's law, you would expect that current would just behave like this, right? So let me draw it here. So you would expect that current would just stay constant, and then you would expect that it will just drop dead almost, right? So first constant current, and then you would think that it will just go down instantaneously. Again, if you don't know this. But now, once we discuss this, now you should be careful. Any circuit, any piece of wire, any element has a certain amount of inductance. Small, but it has. Right? And most of the circuits has some inductors. And of course, all those inductors, if you try to open the switch, so current going up. Okay, let me, different situation, damn it. It's a, okay. So let's assume this current first, there was no current, and then you close the switch. It's the opposite situation, right? So close the switch, and current will, if you don't know this, you would expect that current will go just straight up. But because any circuit has some amount of inductance, and all that inductance will respond in this way. It feels that, okay, damn it, you're trying to increase current through us, right? And it will start driving induced current in the opposite direction to suppress this growth. And as a result, current will go slower, right? It wouldn't be a sharp transition. Nature in general doesn't like sharp changes. Every time there will be some secondary mechanism which will try to suppress the growth, and as a result, overall behavior will be smooth. Right? Nature doesn't like sudden changes. So that's the first situation. Means the second. That was the first. Now the second, and now the last one. So let me put a new bullet. So now, if current is going down. Of course, in that case, di over dt is negative, right? So this derivative is negative. Right? So minus here, minus from this derivative, rate of change of the current. So as a result, delta V is positive. So here delta V was negative, but now delta V is positive, right? So let me separate this as well. So now delta V is positive, and it means now that V final is going to have larger potential, than V initial. So now let me draw a similar picture. Right, so there will be a solenoid. Okay, so battery which drives that original current. So use blue, yeah. So that's our I original. This is again our final point, initial point, right? So NV final is larger than V initial. Electric potential at this point is higher, so I can put now here plus and here minus. Here we have minus plus, but now we have plus minus. And again, why again I introduce this effectively additional battery, because as I said, very often students just see plus here, minus there, and drive the induced current from plus to minus through the solenoid. No, 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 no. This plus and minus is produced in this whole solenoid. This plus and minus is produced in the inside of that solenoid, and then induced current will flow through the rest of the circuit. In order to avoid the typical mistakes, typical mistake I noticed in the past. So I usually say, okay, let's draw this small battery. So now here plus, here minus, and of course when you draw it like this, you don't have an option of driving induced current in the wrong direction. So now of course there will be, this will be the induced current, I induced. Okay, so now original current clockwise, induced current also clockwise in the same direction. So now we can again adjust that Lenz's rule for this system. So if original current is dying, now system, the solenoid, oh you poor thing, you're dying, I don't like it. The solenoid wants to keep current constant. In that case it doesn't do anything, it will be completely happy. But now original current is dying and the solenoid is not happy, and now it's trying to support the dying current by producing the proper potential difference so that the induced current will be in the same direction as the original current. So basically the Lenz's rule we completely restated for situations like this. Right. Okay, so now let me write the rule. So the rule, so which way I wrote it, I induced supports I original again. If current is dying, the system becomes supportive. If current is growing, the system rebels, trying to suppress the growing current. But again, strictly speaking, it's just a Lenz's rule behind all this. It's just system more complicated. It consists not just of one loop when we apply Lenz's rule. Now we have what, thousands of loops stuck in order. Right, so, yeah, and the example similar to this, right? So if you have a circuit, a loop in the circuit, and current is dying. So first, if you have a current in the loop, and if you open the switch in the circuit, and if you open the switch again, if you don't know this physics, you would expect that current will just go straight down, time and current. So you would expect that current will behave like this. Again, any circuit has some amount of inductance, and all that inductance, if it feels that current is dying, it will produce the corresponding potential difference and start driving induced current in the same direction as the original current to support dying current. And again, at the expense of the energy stored inside of the solenoid. Right, so as a result, current will behave something like this. And that's why if you buy some cheap, for example, function generator or pulse generator, right, in experimental physics, in engineering, right, if you buy a cheap one, you're not going to have sharp pulses. There will be, if you zoom in, right, on the at the beginning of the pulse, there will be kind of you will have kind of it will grow, the pulse will grow reasonably slow with lots of ripples if you look closer, right? And of course at the end of the pulse also you will have kind of a not very sharp transition of the current from maximum to minimum, right? There will be some kind of slope with lots of ripples, right? So in order to have reasonably sharp pulses, you have to spend tons of money and buy a very good pulse generator, right? Because yeah, inductance is everywhere, giving us those troubles, right? And In order to find them, you have to spend tons of money. So first, let's discuss conceptually, because these conceptual questions I give on the exams quite often. So conceptual question 11, CQ 11, and I think it's a part C. Right. So we need to understand what happens to the original current if this is given. So let me draw a solenoid. Enough. So let's say this is a solenoid. Inductance L 2 Henry H. Then absolute value of the potential difference across this solenoid is given, and that is 2 volts. Then original current, I will use the same color, blue for example. Direction of the original current is this way. And here in the book it's called I1. Instead of I, just I1. Okay, it's not a big deal. Then, also given the response of the solenoid. So something happens to this original current. It might stay constant, or increases or decreases. That's what. Something happens. And as a result, the solenoid responds. The solenoid responds with this polarity. So plus at the exit of the solenoid and minus at the entrance of the solenoid. So there are higher potential solenoid creates and lower potential at the end. So we need to answer the question, what happens to this original current? So what happens to I1? Okay, so we just need to remember these rules. Solenoid doesn't like changes in the current. If current increases, it drives the induced current in the opposite direction. If original current decreases, the solenoid drives the current, induced current, in the same direction as the original current. So now we see the response of the solenoid. Plus minus. So again, I can draw some small effective battery, right? With this polarity. And now I don't like that this delta V is in my way. I feel like now I need the space. Okay, let me. So I can draw. So it will behave like this, right? So plus minus, right? And of course, this battery, effective battery, will start driving induced current in which direction? That way. I can actually complete, for example, let's imagine that over here there is a no, the opposite way. It will be this way. So this original current, we can imagine, is produced by this battery, and I can add all the time, right? In order to make a smooth discussions. So I1 is produced by this battery. So then something happens to this current, and as a result, solenoid responds with that polarity. So plus and minus. So it means that the solenoid will start driving its own induced current in which direction? From plus through the rest of the circuit to that minus. So this will be I induced. Right? Because again, here plus minus. So it means that current will flow this way from plus to minus. So now you see that induced current and original current directions are the same. So if directions are the same, it means that our original current is dying. So it means that I1 is going down in time because I induced is in the same direction as the original current. So that's how you should run this analysis, right? If you see the response of the solenoid, sort of imagine small battery and draw a direction of the induced current. If that direction is the same as the direction of the original current, it means that the original current is dying. Right? Okay, let me write something about this. So I induced is in the same direction as I original, okay, I1 original. So we can say that I1 is going down in time. Of course. Quite often on the final exam I give questions like this, right? And quite often lots of troubles. Although it's just basically a two-line sort of speculations analysis, right? So you just need to practice by yourself a little bit, right? Or come to office hours, we can practice more, and it's quite straightforward. But again, as I'm saying, on the exam, lots of troubles with that. So now another example, similar to this. Let's say we have. Actually, we can also calculate di over dt. Let's calculate maybe for this example. Let's calculate also what will be the rate of change di1 over dt. Right. Okay, so let's do it. Again, you remember what I erased? So we had delta V equals to what? 2 volts? Yeah, 2 volts. Right, 2 volts. Okay, so from the formula which we derived, there it is. So delta V equals minus L di over dt, and again, that's what we need. We need to find di over dt. Right, so from here we can get that di over dt equals to minus delta V over L. Inductance is given 2 Henry. Right? And delta V, be careful. Okay, here it's good because delta V, it's a V final. This is the final point at the end of the solenoid in terms of the direction of the original current. So since I enters this way, so this is the initial point, exits that way, so it means that that's the final point. So in this case, it will be minus 2 volts divided by 2 Henry. It will be minus 1 amps per second. Amps per second. Right. Yeah, that's the correct answer. Okay, now the next example. Let me put here first bullet, here the second bullet. Next example, let's say we have this solenoid, and what is given? L equals to 1 Henry. 1, yeah. Then delta V equals to, again I can say absolute value of delta V equals to 3 volts. Again, it's a delta V produced by the solenoid across the solenoid. It's not delta V of this battery. That's what is produced by the solenoid. Right, and so we know direction of the original current, and direction of the original current this way. Yeah. Okay, let me use still I1 since it was in the first picture, I1. So that's the original current. Let me emphasize, so that's which creates all this mess. Okay, and then something happens to this original current which we don't know, but we know the response of the solenoid. We know what solenoid does. So the solenoid creates lower potential over here and higher potential at the entrance. Again, so we need to find out what happens to that current. Again, in order to avoid getting the wrong direction, I would just draw a small battery with this polarity. And again, let me also sort of complete this circuit, right? So let's assume that this no, wrong direction. This battery produced the original current. So now this effective battery of this solenoid will drive the current in which way? Through the circuit from this plus to this minus. So it will be like this. So this will be I induced. And now let's look at the directions. Original current counterclockwise, induced current clockwise. Directions are opposite. Opposite direction happens when original current is increasing. Current increasing, solenoid doesn't like it and it will try to suppress it. Driving the induced current in the opposite direction. So in this case, di over dt, current increases. In the first case it was decreasing, now increases. So now let me write that down. So I induced is in the opposite direction. To I1, so it means that I1 is increasing in time. So it means I1 is increasing in time. And now let's calculate di over dt. So di1 over dt, similar, it will be just minus delta v over L. Now with delta v you have to be careful, because what I gave delta v absolute value 3 volts. But now we have to get the correct sign. This is the final point. Again, let me emphasize on that. So this is the final point. This is initial point. So delta v, okay, I will use even blue, so it's a v final minus v initial. Minus and divided by L. So in our case, final is at lower potential, initial at the higher potential. So this delta V is negative, so we will have to write minus 3 volts. Minus 3 divided by L. So it will be minus 3 volts divided by 1 Henry. So now we are getting positive current. So here we got the fact that current increases conceptually, and now we can get it mathematically, right? So it will be 3 amps per second. Okay, again, practice it by yourself a little bit, right? So if you still strike them, only 2 situations. Current increases or current decreases, right? Current increases in the case when induced and original currents are in the opposite directions, and current decreasing, like in that situation, if currents are in the same direction. If you need more help from me playing with this, come to office hours. We can discuss tomorrow from 2 to 3, or just shoot me a mail. Okay, so now another problem. You just need to get used to a new form of Lenz's rule, where you have to play with current, not the flux. Okay, let me at least discuss one more problem. I need to erase this, yeah. Okay, at least I erase the top. So problem 25. Yeah, chapter 30, problem 25. Again, there is a solenoid inductor. There is an inductor. So let me grab my notes. So we have an inductor. Inductance is given, I think, yeah. 10 millihenry. Then there is an inductor, and of course there is a current flowing through that inductor. We know some information about that current. So we know that initial current is 150 milliamps. Yeah, milliamps. And then that current goes to final, which is 50 milliamps. This is information about this original current, right? It changes in time, so final and initial. Right, and these changes in the current happens in this period of time. Delta t, 10 microseconds. So we need to find what potential difference created by a solenoid in this case. You see, current changes, original current changes. So of course the solenoid will respond with will produce its own potential difference. Because again, you remember, it doesn't like when current changes. If current doesn't change, it doesn't do anything. But if current does change, then of course the solenoid will start producing delta V. So we need to find delta V. And again, let me emphasize, produced by a solenoid. Oops. Produced by the inductor. L. Yeah. Again, we can discuss conceptually what will be the sign of delta V, positive or negative. It shouldn't be difficult, right? So I can probably draw the picture like this. So let's say that's the battery which produced this original current, which is, it looks like it's dying, right? You see 150 and then 50, so the original current is going down. So that's the original current, original, right? And then we know this time we know information about what happens to the current, right? So now if current is dying, where is our analysis? Current is dying, so it means that induced current must be in the same direction as the original current. So our induced current must be in the same direction. So induced current must flow this way. So this should be I induced. You see, both cases clockwise. So in order to get this induced current, let's draw this effective battery which could drive this current, induced current. So of course it should be here we should have plus and here minus. So plus minus in that case, yeah, current will be that way. So it means that at the final point, this is the final point, we have higher potential. At the initial point we have low potential. So delta V must be positive. Delta V must be positive. Right? So let's get it anyway mathematically, because we have the formula, and let's calculate that anyway. But first I want to discuss conceptually, because again, it's all about this. Supporting flux or suppressing, not flux, current. Supporting or suppressing the current. So now let's calculate. Right. I will put a bullet. So delta V equals to minus L di over dt. And now at this point I have to pause, open my explanation box, and I have to make a statement. This problem is not stated completely. One piece of information is missing. We have di over dt, basically derivative of current with time, right? And we don't know how this current changes in time? Is it changing linearly, or maybe exponentially, or maybe somehow else complicated way? That piece of information is not given. Of course, we understand that the author tacitly assumed that current changes linearly, but you need to state it. You need to state it, and this piece of information is missing in the problem, right? So, which is not completely good, right? Not good. All right. So, as a result, I will write. So, assume this current changes linearly. Without this assumption, what I'm going to write next kind of doesn't make sense. It wouldn't be correct. It wouldn't be correct. So now, if current changes linearly, of course, di over dt can be replaced with what? With delta I over delta t. We've done it already several times in this semester. Because the slope, if you have a straight line, it doesn't matter if you use infinitesimally small di to calculate the slope, or finite delta I to calculate the slope, it will be the same. So, minus L delta I over delta t. Okay. So now after this additional piece of information, now we can just basically plug the numbers. Alright, so it will be minus L, and of course delta I, it's I final minus I initial divided by delta t. Okay, so now let me plug numbers. Probably I should put brackets to make it look better. So L 10 times 10 to the power of minus 3 Henry inductance. Final 50. Initial minus 150. And let me multiply it times 10 to the power of minus 3 amps. Milliamps, so 10 to the power of minus 3. I just factor it out. And divided by this stretch of time over which this transition of the current happens. So delta t, it's a 10 times a micro, it's a 10 to the power of minus 6. So minus in front, minus because current is going down, so this gives you a number, negative number, and so as a result your delta V is going to be positive. And we got delta V, positive delta V, analyzing this conceptually. Alright, so if you calculate it, you will get plus, of course, 100 volts, 100 volts. Actually, this basically process is used to ignite the gas in the engine, car engine, right? So there are solenoids. You change the current. Suddenly, there is a large potential difference is created. So it creates the spark, and the gas burns in the engine. Okay, so guys, the next problem is, okay, let me erase this, is even easier. And so we don't have time, so I will just discuss it quickly. And I will send you my solutions. You should be able to understand it easily. So now, in the next problem, plot is given how current changes in time. So it's a problem 66. So something like this. Let's say you have current I versus time. In current, for example, first is growing, then stays constant, then is going down, and then stays constant. Let's say it this way. So you need to get how delta V changes over time. Again, so we have an inductor, solenoid, and through that solenoid, this is the current going through that solenoid. So first current increases, then it stays constant, then decreases, then again stays constant. Of course, you see current at some point, some stretches of time changes. So according to all these, there will be potential differences across the solenoid, positive or negative, right, bigger or smaller. So you need to plot that delta V. So what you have to do? So let me just hold you for a second. You need to split this into 4 regions where current is constant and analyze it. So again, using this formula, so you need to you just need to find delta V. Inductance is given, so you just need to find the slope, di over dt for each part. Slope over here. Who cannot find the slope over a straight line? Of course, all of you can do that. And of course, in this case, slope will be positive. Slope positive, minus in front, L is given. Of course, you will calculate delta V, and delta V will be negative. Then, for the second stretch, what's the value of the slope for this part? 0. Delta V will be 0. So this situation, if current constant, the solenoid is happy and it doesn't do anything. Then, this case, current is going down. Calculate the slope. Slope will be negative. Negative slope, minus over here, value of L is given, so delta V is going to be positive. Again, you can easily calculate it and plot it over here. So over that stretch of time, delta V is negative, then 0, then positive, then again 0 over here, right? So the problem is banal. Right? So I will send you my solutions, right? I also was planning to discuss, I thought we will go a little bit faster, but I didn't feel like rushing through this analysis. So as a result, I did not. So I thought about solving the quiz, but I will just probably post my solutions to the Blackboard, probably by the end of today. Okay, guys. So if you have questions, go ahead, and I will answer. Otherwise, I will see you tomorrow. There will be a lecture and also office hours in the second half.